as we near the end of our unit on vector valued functions, I'm going to take a look at an example that might have been covered in a second semester calculus course, but we're going to look at it from a vector function perspective. So we're going to do an arc length calculation, and to calculate the arc length we are going to use the formula that the book's been generating for us, lowercase or small s equals definite integral, whatever the t boundaries are or time boundaries, magnitude of the velocity vector with respect to t. That's our formula. So we need a vector valued function for this function here, and y equals x squared is, for many of us, the algebra for the first nonlinear function we ever saw. Looking something like this, centered at, vertex at the origin, opens up, all kinds of fun things we've learned about this. We are going to be investigating the length of the curve from here to here. So when x is 0 to x is 3. There is a function of a single variable way of approaching this, frequently covered in second semester calculus. That's not the method we're going to use. We're going to use our vector function knowledge. So we need the vector function, and we have seen that if you have a simple y equals function, you could just set x equal to t and then y equals whatever the function of t is. In this case it would be t squared. And as we can see from our graph, since x goes from 0 to 3, well, that means that t goes from 0 to 3. So we have our t boundaries, and before too long we'll have the magnitude of our velocity vector. So velocity vector would be the first derivative. Derivative of t is 1, and derivative of t squared is 2t. So we are cruising along here, and I'm just going to put the magnitude directly into our integration formula, which is going to look like from 0 to 3 square root 1 squared plus 2t squared dt. This integration, even though it may look simple, it's not a basic integration formula, and u substitution does not work. If u were equal to 1 plus 4t squared, you would need at least a factor of t outside of the root in order for this to work quickly by what's sometimes called in the Western world u substitution. So if this were second semester calculus, the next 30 minutes of our time, or 20 minutes of our time, whatever that time would be spent looking at integration techniques, trigonometric substitution being among those. What we're going to do is use another tool from second semester calculus, but may not be used as frequently, and we are going to look how to integrate this by just finding a formula in the back of our calculus book or in some sort of a calculus source that might integrate that type of function. And it turns out that I have one of these ready to go from the back of my calculus book. If you have some function squared plus some constant squared in the root with respect to that function, then this is how this expression would integrate using a variety of calculus 2 techniques that would take a lot of time. So how hard is it to just use one of these formulas? I mean, I just plug it in, right? I think it's not going to be very difficult, but I don't think it's instantaneous answer either. There's some little pieces that you want to show. For instance, That's the function variable, and this is the constant, and those are written in reverse order here. Not difficult, but I have to pay attention. So it would appear that the constant would be equal to 1, and the u would be equal to 2t, so that would be u squared. And then what about du? Well, that would be 2 multiplied by dt, and if I want to know what dt is, I guess that would be du divided by 2. So I have dt, I can replace dt with this. This is going to become u squared, and that'll be 1 squared, or a squared as the formula says. Alright, let's fill in the blanks. Let's fill in all of these blanks. Now, I've taken the liberty of doing this in advance because it's long and messy, but I will just slide this paper up here and try to keep this on the screen for a moment longer. Alright, so first thing that happens is, oh well, look at that, I just sort of filled it all in. I took all the fun from you unless you hit pause before. Or maybe you should pause, rewind, and try filling it in yourself. But to save us time here, wherever it says u, I rewrite the statement as 2t. Wherever it says a, I rewrite 1. This 1/2 is part of the formula here, but if you look at what I've written here, there's an extra factor of 1/2, and I've written it in red if your screen shows that. That 1/2 is actually the 1/2 here, because dt became du divided by 2, and this is the 1/2 but factored out of the integration. And now I get to evaluate this from t equals 0 to 3. Let's see what happens with that. Alright, when t is 3, I get 2 times 3 is 6, 3 squared is 9, times 4 is 36, plus 1, 37, and I get something similar over here when I plug in t is 3. And then when I let t equal 0, this expression becomes 0. 2 times 0 is 0. 0 plus 1 is 1, so I wrote it so you could see that I didn't ignore it, that I took it into consideration. Alright. Finally, let's see what happens here. Well, what happened? Looks like I erased half of my previous work. No, I didn't. The square root of 1 is 1, and the natural log of 1 is equal to 0. This function can be evaluated. In my classroom, if I don't provide a calculator for exams or quizzes, I have my students evaluate functions whenever possible. So I do not know what the natural log of 6 plus the square root of 37 is, but I do know what the natural log of 1 is. So this entire half of the expression was 0. And since I'm not going to provide calculator for this particular type of problem on my next unit test, this is how my students would leave the solution. Certainly if there was a calculator involved, you would go another step and get a decimal approximation. One last feature I feel like I should point out. Note that the absolute value disappeared from my formula, and that's because 6 plus the square root of 37 is positive, so I don't require absolute values if I already know the expression is positive. Alrighty, not pretty, but it can be computed. That is the length of the x squared curve from 0 to 3 on the x-axis. I'm sure you would have guessed that if you didn't have this calculus class, huh? Until next time.